So, hi everyone. So, first of all, thank you very much, Elaine, for visiting us and for being here during the seminar for everyone, and all of you for attending the seminar. So, that's the title. Elaine will be speaking about surrogate modeling with sort of approach to probabilistic hazard assessment. And sort of to introduce Elaine to all of you, she's Claire Booth Lucy, you say? Luz, professor of applied mathematics and statistics at Marquette University in the United States, so in Milwaukee, Wisconsin. She has more than 20 years of experience in statistical modeling and uncertainty quantification. She obtained her PhD in applied maths from Northwestern University in Illinois. And then from 2005 to 2008, she held postdoctoral positions at the University at Buffalo in New York, and CMC, which stands for Statistical and Applied Mathematical Sciences Institute in North Carolina. And then she joined Marquette University in 2008. She has been assistant chair of the Society for Industrial and Applied Mathematics activity groups on uncertainty quantification, and also mathematics of planet Earth. She's a member of SIAM, the American Statistical Association, and also she's a volcanologist in heart. So she's a member of IAFSI as well. She has, as I said, more than 15 plus years of leading or co-developing novel strategies for probabilistic volcanic hazard assessment, including some of the ones that you'll see in here. And she's been doing her work mostly in Montserrat in the Eastern Caribbean, in California, Long Valley Caldera, for instance, in Ethiopia. We've been working together at Luto Volcano, and now at Fuego in Guatemala. So it's a great pleasure to have you. It's a great pleasure to work with you. And yeah, I hope that we continue to work in the future.
Thanks. It's great to be here. Thanks for your hospitality for having me here for the next 6 weeks or so. Happy to tell you about my work. So thanks for the invite. Tell you about some strategies for surrogate-based probabilistic hazard assessment. And really, this applies for all kinds of geophysical flows. So Milwaukee is where I live. So this is gonna be tricky. So here's Milwaukee. It's sort of toward the southeast of the state of Wisconsin. Chicago is just on the other side of the border here, so just south of us. Lake Michigan is over there, and we're in the upper U.S. Right. So that's where I'm from. And all of this work, as Pablo alluded to, is really not possible without a lot of different kinds of researchers collaborating together. So you're just some of my collaborators. I did not mean to do that. Do you know how? I held it too long, I think. Perfect. So here are some of my collaborators, and a lot of the work I've done with Pablo is through this ISHEL project. Of course, just like many projects, the funding is done, but the work continues. And I wanted to, so my PhD isn't related at all to geophysics or volcanology. And really, when I got into this as a postdoc, it was this idea of rare events that I was interested in. And so I always thought this quote was interesting. So this is from Mount Pelee in Martinique. And it said 100 years ago, government officials in Martinique made the mistake of assuming that despite signs to the contrary, Mount Pelee would behave in 1902 as it had 50 years previous. When a rain of ash they considered to be a benign volcano surprised, but did not harm those living under its shadow. And I think this is really sort of gets to why we need to take a probabilistic approach to what can happen with geophysical hazards. Because often, especially if you've lived with the hazard, you feel like you know it. In a lot of ways, you do know it, but there's still a relatively high probability that something of a larger scale could happen that you may be unprepared for. And this isn't specific to PDCs. We could do a similar sort of analyses for lahars. Also could do a similar sort of analyses for storm surge from volcanoes, right? All of these are really described by a similar set of conservation partial differential equations. I say the hard thing about storm surge is the uncertainty is really in the storm track itself, which is quite challenging to model. So I'm really going to focus in this talk on PDCs and on post-fire debris flows. So this is from the Thomas Fire in Southern California. And this 2 billion number is really from the debris flow, not from the fire itself. Because I know that this photo is a bit grainy, but this is a very posh area of Southern California. So Oprah and Prince Harry live in this neighborhood. So houses being destroyed there is a lot of money. But because it's so posh, it's also one of the best prepared to deal with this. And that's a lot of what we want to think about, how to think about being ready for the secondary hazard when a fire happens, right? Before the fire happens, ultimately. Okay, and a lot of the sort of state of the art for post-fire debris flow modeling was sort of giving us, I did it again. Okay, that goes back though, good. Was giving us this, giving us a sense of where the debris flows might happen, right? But really what we're interested in is if they happen, where do they go, right? And who's going to be impacted? Okay, so there's some commonalities for these different kinds of flows. There's these complicated spatially varying footprints. There's a lot of aleatory uncertainty, how big, how strong, where, when, and these are things we really should be describing probabilistically. And then of course it's the rare events, that we're concerned with typically, because those are the ones that are going to lead to catastrophic outcomes. Because small scale events happen all the time. And again, I'm going to focus on PDCs and debris flows. All right, so here's so Montserrat in the Caribbean is has a ton of data, really well documented volcano. And here was an annualized rate of events, and this is events from roughly 1995 to 2010 or so. And on the horizontal axis, we're looking at the log of volume, right? So we can say, oh, well, that looks roughly like a line, right? That looks roughly like a line. And we can model that, right? We can model that with a probability density function down here. And really the parameter we're interested in then is what is that slope of that line? All right, so this is that particular model happens to have heavy tails. So I just want to think about why we'd want to consider what happens with heavy tails versus maybe a not heavy tail distribution. So if you consider a record of 10 volumes, a non-heavy tail distribution, like maybe an exponential, if you're looking that the 11th volume is an order of magnitude bigger than the 10 in your record, it might be something like 1 in 200,000. Where the heavy tail distribution, the probability that the next event is an order of magnitude bigger is maybe more like 1 in 100, right? So if your data follow a heavy tail distribution, you really need to be accounting for those larger than in the record, but still quite probable events that you might not have encountered before. Okay, and then really what we're interested in is what is the inundation footprint of this order of magnitude larger flow. All right, so there's some commonalities for geohazards. So often, physics is what we have to do this exploration. So computer models for these flows are hyperbolic partial differential equations, basically a shallow water type equation with some additional terms. And I'm going to try not to do that again. They're solved over a digital elevation model, and ultimately they're computationally intensive. Maybe on the order of 20 minutes on a big HPC for a small domain up to, a few days. And then there's epistemic uncertainty. These models are not perfect. The probability density we fit to that data is not perfect. So we're introducing, in our modeling process, we're introducing more uncertainty. And then there's what I call structural uncertainty, which I'm not necessarily going to address today, but you'd be remiss to not mention it, where we'd like to know how well the models capture reality, right? Because often, we want to address questions about the world we're living in and not, what we do on the computer. Okay, so here, these are, so physical processes of flowing mass. So this is the equations that Titan solves. And so we have continuity of mass and momentum. That's one of my colleagues says that a little box that conserves stuff, right? Stuff in has to go out. And here for this rheology, we have gravity pulling us down, and then we have friction between the grains and friction between the flowing material and the bed driving or slowing the flows down. Right, so this is our typical PDE. We'll look at another, I'm not going to show equations, but another rheology, but basically similar flavor where, what you're doing on the right-hand side changes, right? What sort of rheologies you're assuming. Okay, so here at Montserrat on the left, this is what our data sets look like. So we have records of which valleys the flows went down. And so you can basically infer angles for the initiation of the flow. We have that same volume frequency data. And then we also have this mobility data. So we have H over L here versus volume. And basically, if this unfortunate phenomenon that larger volume flows are more mobile, right? So now if we're thinking about these are things we can turn the knob on when we run our Titan 2D simulation. Well, then here's just 4 snapshots of what we might get out from, doing that strange, from Titan, right? And they look pretty different. There's quite different footprints in those 4 simulations. And none of them are really very large in volume there. All right, so what we want to do in a hazard assessment, well, we want to know the probability of inundation. And so here I have this indicator function that says, oh, yeah, the location I'm thinking about was inundated. And then it's 1, it's 0 if not. And we'd like to integrate this over all our scenario, right? Say possible volumes, possible angles. And then we also parameters that are in those aleatory distributions, like the slope of the volume distribution. Well, that thing is also uncertain, right? So we might want to consider integrating out or averaging out over epistemic uncertainties as well. So that's one thing we want to do. Another thing we want to do is, well, maybe we're really interested in what does inundation look like as a very one parameter, right? As a very volume or as I scan angle. And you can do something similar there where you integrate over all the other parameters, right? And then you can say, okay, well, I'm accounting for the uncertainty, other parameters if I do this integration, and I can look at, well, what is this? What is the flow depth or as a function of volume, say? Okay, so here's my cartoon of Monte Carlo, right? So we want to know the probability of some physical scenario. So it has some distribution. And how we explore it is by sampling, right? So on the horizontal axis, we have samples. And then there's some scenario that leads to catastrophe. And that's really what we are interested in. And so here we say, okay, with our Monte Carlo, well, 4 out of these 30 samples are catastrophic. And Pablo is much too nice to do this, but our collaborator, Robert, might be like, well, that's That's the wrong choice. You really should have been sampling from this other distribution. And if you're doing naive Monte Carlo, you'd have to repeat your process, right? And if each of these simulations is minutes to hours to run, right, that's quite expensive. And there are other games you can play, but and we'll talk about this later. But the key is that you really sort of need to know where that boundary is. That's really the game here. Okay. And so these things we want to do, right? Finding the probability of inundation or looking at how inundation varies as we vary our inputs. These are expensive calculations, and the key to, and hence the title of this talk, is getting a cheap approximation of the inundation for whatever kind of scenario that we're interested in. Okay, so now I want to think about, right? So I know a lot of us are physical modelers. I guess I started out that way myself. Where you have a PD or an OD, some state that you're interested in how it changes over space and time. You have a bunch of initial conditions and boundary conditions. But the mapping we're looking for is really a mapping of initial conditions, boundary conditions, parameters to some output quantity of interest. Maybe it's the state or maybe it's some functional of the state. Right. And then in the language of uncertainty quantification, we have some computer model that maps inputs to outputs, right? So inputs are sort of getting at the scenarios that we want to look at, and outputs are was this location inundated or not, say, or the depth of inundation. All right, so this is ultimately we're calculating averages, right? We're calculating expectations. And what you'd want to do though is predict this computer model output with uncertainty using a relatively small set of training data. And the idea to do this is to view the computer model as a realization of a random process, and specifically we'll look at Gaussian processes. So this is a strategy that goes back several decades now. And a lot of the work that's been done is really just trying to relax assumptions and trying to make things, trying to build surrogates that are appropriate for your data set, whatever that is. And so these are sort of the OG works, but these two down here are recent books that are quite good summaries, and particularly the Gramercy book is available as a PDF if you're interested. Okay, so here's our sort of cartoon of random functions and modeling with random functions. So we can only draw things in 1D basically. So I have my inputs X and my outputs Y. And we're hoping that the relationship we're trying to learn between inputs and outputs looks like a random function. So maybe it's this bold green curve. And I just want to emphasize here that this functional relationship is nonlinear, or can be quite nonlinear, even though we're working with Gaussian. And often when we think Gaussian, we think linear, right? Because we think like data assimilation or something, where Gaussians have a hard time describing nonlinear phenomenon. But for this relationship, where the Gaussian comes in is if we look at one input and take a profile, that distribution over our output space is a Gaussian. Right, so that, let's go back here. Right, so if I look at, this slice here and turn it on its side, I have this Gaussian profile. And so this is, now we're modeling our output as a Gaussian process, or we will, but here we're just looking at priors on Gaussian processes. So I might have some trend function, often constant or linear, and then with a zero mean Gaussian process. So it has a scale of scalar variance that just tells us how wide this is. Or if we go back, it tells us about the vertical scale here. But really what we're interested in, and then at one particular input, it's just a Gaussian, but really what we're interested in is learning about this correlation structure. As you have a nearby input in scenario space, how is it correlated to other inputs? Right? And this is really the work of fitting Gaussian processes or fitting these sorts of statistical surrogates. So here's a cartoon to do it. So here I have 8 computer model runs from some toy function. And so my inputs are X and my outputs are Y. And now I'm not going to consider all random functions. I'm just going to consider those that are conditioned to go through or maybe near my my computer model design and responses. Right. So these are the sorts of random functions that are candidates now for describing this model. All right. And basically here, the gist of this is in finding the correlation structure for a given data set, so you have these correlation lengths, gamma here, and you have this likelihood function. So this is a Gaussian likelihood function. This can be, especially if you have a decent amount of data, a really hard problem to optimize with maximum likelihood estimation. So instead, we assume some prior distributions and look at a maximum a posteriori estimate of that posterior distribution. And this is work by Mingyang Gu and Jim Berger. Okay, so assuming we have that, now we have a predictive mean of the Gaussian process. We have those correlation lengths in our other parameters. And we have our standard error. And I'm not really going to get into it much, but basically the capital R is a correlation between all of your training inputs. And the little r is a correlation between your untested input, X star, and all of your training inputs. Right, so we have this predictive mean and this predictive variance. And now if we look at a sort of cartoon, this is what those equations are giving us. Right, so we have this predictive mean here is effectively an interpolator. And so I can go down at some untested input, say 0, and say, okay, well, I have my estimate of this model. But I also have an estimate here of the uncertainty that I'm introducing by using the surrogate in place of the simulations themselves, right? That's going to be given by that standard error, which we can get like, say 95% credible intervals for, which is what those red bands are. Okay, so that's what we're looking at. And now, right, we're going to do this for flow simulations. Right, so we're going to generate a training set of flow simulations that are spread out over input space. Typically, we use a Latin hypercube design. And for each pixel, we're going to construct a Gaussian process emulator of the inundation depth. And then we can sample random scenarios from our aleatory model, or perhaps our epistemic model as well to calculate the probability of inundation. Right, and I want to look at this process of some probabilistic hazard maps on Montserrat. One thing I want to mention in this paper, there's a lot of work that goes into this aleatory distribution that I'm not going to talk about today. In particular, thinking about, because this is Montserrat's been relatively quiet since 2010, and so we did some modeling for thinking about the long-term frequency of possible PDCs at Montserrat. So that's wrapped up in here. But what we're going to look at now is thinking about varying the density of the angle, right? Which valley does the flow go down? So here's if we assume it's uniform. And so we're looking at 1 years, 5 years, and 20 years. And now we have probability contours in black here. So 100th, 1,000th, the 10,000th, et cetera. And then we can sort of watch how those evolve with time under this frequency model that I've not told you about. And now we can say, well, what if we just think about flows that go east? Most of the flows go east because there's kind of a horseshoe at the top of the crater. And here's sort of the equivalent hazard maps. Once the original simulations are done, these again were in Titan, making a map is about 5 minutes on the laptop, right? So it's quite quick. And let's go this way. And really, what I want to get to is this is an approach where there's not going to be one map as an answer, but really a family of maps to explore what's going on under different probabilistic scenarios. Oh, and then, sorry, I didn't look at this last one. So this last one is, I'm not good at this. This last one is if we're looking at the density just going northwest. And the northwest bit of that valley there is sort of where they're doing a bunch of mining, which is now one of the bigger industries on Montserrat. And so thinking about the safety of people and equipment that are there. Okay, so a little bit of an aside on calculating rare probabilities of rare events, right? So you just want to think about an experiment where we flip a coin 100 times, and if it's heads, we step to the right. If it's tails, we step to the left. And X is our final position. And if we wanted to look at the probability that we go 70 steps to the right. Well, it's binomial, so we could calculate it exactly, but to simulate it, you'd be running it the rest of your life, right, on your laptop, and you'd probably never see one of these walks that got to 70. So the trick here, though, is to use a biased coin, right? And if we think about this, if we were to use a biased coin that walked to the right, or gave you heads 85% of the time and tails 15% of the time, you'd end up often right around here, right? So here's what that would look like with a bias coin. And what you can do is you can say, oh, what was the probability of getting that event if I had used the fair coin? So you can correct using the bias coin with a likelihood ratio, or if you're fancy, or something called a radon-Nikodym derivative. But basically now you can simulate really rare events. But the key is you have to know where the target is. Because if you miss the target, if you overshoot, say, so here I'm taking 95 steps, a probability of heads is 95 and tails is 5%, and I overshoot, and now I have an estimate that's 3 orders of magnitude off. Right, so I have a bad estimator if you don't capture this sort of threshold between your rare event happening and not. All right, so I want to go back to thinking about these maps and why doing sort of resampling strategies, which is a good strategy, something you should be doing often, but it doesn't really work in these cases because each of the probabilities over here, so green is low to red, so 0 to red is 1. Each of those would take a different sampling strategy because they have different thresholds of inundation, right? So really what we need are surrogates that can faithfully model thresholds at each map point. And that's going to bring me to some work with Pablo. So this is a couple of simulations at Aludo volcano. I'm going to sort of trace this because it's hard to see the boundary. So this is the larger simulation. This is the one that's centered. So simulation 1 centered at the triangle. And then I have the smaller simulation 2, with its boundary over here. And we're just focusing on these two. There's a road that goes sort of between here, and we're focusing on these 2 road points. And really, in my mind, the point of this picture is to get at, simulation 1 inundates both of those road points. And simulation 2 inundates neither of them. But the zeros are different, right? Because simulation 2 almost gets this road point, and it misses this one by a long shot, right? So we want to be thinking about those. They're both 0 in the data set, but they're really kind of, there's quite different behavior there. And here this was Titan again, but with a flux source. And so our inputs were the vent opening location, the volume through vent radius and flux, and the mobility with the basal friction. We want to look at the same thing, right? But now really what we're looking for is H to be a faithful approximation near those inundation boundaries. Okay, so here's just a cartoon of the problem, right? So this is just a cartoon function. And you see this a little bit hard to see on the screen here, but there are design points and responses that have pluses if they were positive, and they have circles here if they were 0. Right. And so really what we end up with, and now I'm thinking I have 2 inputs, so X1 and X2. And now what we're thinking about is we have this sort of really strong non-stationarity, that we have this, we're fitting this random function that, you can, is a sort of curvy and smooth. And then we have an irregular boundary to completely flat at 0, right? And that's a very hard thing to fit with a traditional Gaussian process. And in particular, a lot of the strategies that people use to deal with non-stationarity, it might solve it for this particular pixel, but another pixel, I mean, this is a cartoon, but another pixel that had a different inundation boundary, what would happen, right? So it'd be something different. So our approach was to take that last picture here and replace these 0 outputs with negative outputs that are consistent with the Gaussian process fit to the positives, right? So here's a sort of picture we get, right? So each of the negative design points we've replaced, each of the 0 outputs, responses, we've replaced with a negative. And in the end, we're going to take the maximum of this surface in 0, right? So we can reproduce that inundation boundary relatively well. And so here's the algorithm, but it's basically what I just said. So we're going to fit a Gaussian process to the positive outputs. We have to kind of have some initial negative guesses, but then we're going to sort of one at a time take one of these out and then sample it from the surface that's remaining, and then replace that negative with our sample, repeat, and then take the average at the end to get these negative values. And it's a little bit hard to see here, but the real key is, maybe it's better on the last screen, is that this sort of approach is assumed to modeling just a 0 or something positive, and then with a shape to the positive, is that these zeros that are right along the boundary, they correspond to negative values that are quite close to 0, right? Just a bit hidden in this picture here. Okay, so back to Aludo, and this was just to, again, give you this picture of what we're looking at with these 2 road points. And we'll notice that these road points are on either side of a caldera rim here. And here are sort of 3 different approaches to fitting Gaussian processes at those 2 road points. So the top is fitting a Gaussian process only to positive inundation, right? Only to the simulations that inundated. So again, this is road point 1, which was inside the caldera, and road point 2, which was outside. The middle is both the positive and some of the close by zeros to fit your Gaussian process. And the bottom is this is a 0 Gaussian process approach that I just explained. And really the moral of these pictures is that if you don't sort of tell it where it has to go to zero, you end up getting these rebounds outside of your design. And this is really hard to work with if what you're looking for are zero contours for your probability calculations, right? And we see this in both cases. Okay. So then with this approach, we looked at a couple of different vent opening models. So just a uniform vent opening model and a model developed by Ben Clark and Pablo and others. So again, we're thinking about these two road points and now looking at the probability of inundation versus volume for those two road points under these different models. Again, this is a sort of thing that we'd like to be able to explore quickly, right? With the Gaussian processes let us do, and here the ZGP lets us do. And then we can also think about a bit of a probabilistic hazard map here in this sort of small domain, including both of these road points. Okay, so I'm going to switch gears a little bit and talk about post-fire debris flows. Oh, that was supposed to be. Oh no! I forgot. I stuck in some stuff that Pablo and I have been working on this week. So let's go back to Guatemala, and so these are designs for two different models at Guatemala, so Volc Flow and Titan. And basically they have different rheologies. And we have three inputs. So we have volume, and in all four figures, volume is going along the horizontal axis. I have my Titan design on the right and my Volc Flow design on the left. On the top, we're looking at duration versus volume. These are the same design metrics, and just a different set of samples that the simulations were done on. And for Volc Flow, and then we have mobility metrics on the bottom. So for Volc Flow, we have the constant retarding stress, and for Titan, we have the basal friction. This design and basal friction comes from work of Sarah Ogburn that we later employed in my student's thesis for Long Valley, and really we need to avoid this sort of very mobile, smaller volume flows because they get quite unphysical, right? So for smaller volume flows, we want to restrict it to that idea that larger volume flows are more mobile. And then when we get above about 5 million or 50 million cubic meters, things are just in that range there. Okay, so here are our simulations. There's 300 of the Volc Flow simulations and 300 of the Titan simulations. And this is not a probability map, but just under that design, which is meant to cover the space of aleatory distributions that we might be considering. We have these, what we've been referring to as hit count maps. So white is 1, and up to the darkest red is 300. So we can see the Volc Flow is more channelized, and Titan certainly has more overbanking. Now, what we're looking at are these three points of interest, A, B, and C. A, B, and C go from west to east. They're the same points for both flows. And now for those 3 points of interest in each case, we're going to look at the zero contours in volume and the mobility metric. But before I show you that, right, I had these 3 inputs. I also had duration of flows. So what I'm going to do, I have 3 inputs I have to evaluate the Gaussian processes or the ZGPs at. So I'm also going to look at the sort of upper duration curve and lower duration curve. So when you see these, you're not going to see a curve for the zero contour, but a band depending on if it's the upper duration or lower duration. right? And this is what we see. So this is kind of hot off the presses. So in our volume mobility planes in the two cases, right? So Titan on the bottom and Volcflow on the top. A lot going on, so let me just talk you through it. So all of the points were our design run points. The ones that are in black inundated all three locations. The ones that are sort of half sort of gray inundated at least one of those, and the ones that are unfilled didn't inundate any of the three locations. Here we go A, B, C. So again, west to east here. And what's interesting in particular, I think, well, first is that much smaller volumes inundate these locations in bulk flow than in Titan. And for Titan, we're really restricted by the mobility, right? So for just a slightly higher mobility, so like down is more mobile in both cases. For a slightly higher mobility, you need a much bigger volume flow to inundate those locations. But probably particularly of interest is location B here, which for bulk flow is just adjacent to this channel where a lot of simulations are reaching. And in Titan, because there's so much overbanking, a lot of the material just doesn't get down there, right, adjacent to that channel. And so B corresponds to the yellow here. And so we see in bulk flow that is that would be with the bulk flow model quite a dangerous spot. This is only 10 million cubic meters, so less than the 2018 event at Fuego. Although down a different barranca, these are all down a different barranca than the tragedy at Fuego. And yet this is sort of the least take the largest volumes to get to that same spot in Titan, right? So really, this is letting us do a sort of comparison of two different physical models and their implications for hazard. Okay, so now on to something a bit different. So we're looking at debris flows that happen after forest fire. So of course, and probably everyone here knows this, but after a fire, the soil becomes hydrophobic, and it's with the same rainfall, it's much more likely to cause a debris flow can bulk up in order of magnitude over a clear flow, right? That would happen without a fire. Right, so we start to get really fine sediment that goes into the drainages, and then the drainages sort of get scraped up. And of course, we have very fines to boulders here. And so again, the models are quite similar. And I want to point to my colleagues Luke's work here. In my mind, his models versus say DClaw or Titan, sort of a version of Titan like I just talked about, they specify you to put down, they specify a volume of flowing mass, right? You have to say, okay, here's a volume of flowing mass, but there's a huge amount of uncertainty in that, right? A huge amount. And so this is why this is maybe a better modeling approach that includes erosion and topographic change, and erosion that's rainfall driven, right? So that's what this the McGuire models from about 10 years ago do. And right, so again, we want to sort of be thinking about the same things. We have a lot of aleatory variability. We don't know how big or when or where things might happen. The source terms are quite hard to characterize for post-fire debris flows. I think we've sort of gone on the scale of easier to characterize to hard to characterize from Montserrat, which is pretty straightforward, to Aludo, where characterizing the vent opening is quite a chore, to these debris flows where you'd have to assume a volume, basically, right? So we have very high epistemic uncertainties here. And this McGuire model captures the bulking, the physics of the bulking. Okay, so this is a cartoon from his model. So we have the rainfall time series here. We have snapshots of this catchment at 20, 40, and 45 minutes. We have the flow depth over here, the color bar, and on the right, we're looking at the outflow of this drainage and what's happening over time. And really, these post-fire debris flows, it's not so much a lot of water that's the issue for these sort of shallower flows. Deeper flows are a different story that we're not modeling. But for these shallow flows, it's really intense periods of rainfall that cause the bulking. And you can see this here, right around the 40-minute mark. There's very little bulking in the flow depth at the output of the watershed. But we get to the 40-minute mark, the intense rainfall is bulking quite a lot, and we get a lot of flow coming out. And then we get this sort of chugging that's quite commonly observed in practice at the outlet afterwards. If we look at the same picture, but instead of the depth of the flow at the outlet, if we look at the sediment concentration at the outlet, we see that we have basically a clear flow until this high value of rain, and then we get high sediment concentration, and again, this sort of chugging behavior. Okay, so here is a debris flow simulation for this Thomas fire. The flow depth is on, the color map is on a log scale here, but just to see the sort of intricacy, this is about 16.7 million pixels, and we've been building Gaussian processes 1 pixel at a time, which is a problem. And so instead, we're going to employ this parallel partial emulator. And basically, because I've not spent much time on equations, really what I want you to think about is we're looking for, so here we have S pixels and N training runs. Right? So we're assuming a common correlation structure among all the pixels. And so these predictions then just require these relatively small inverses that need to be computed once. And what we have then, basically just a multi-dimensional version of the Gaussian process mean. The computational overhead is just linear in S then. And the one thing that's a bit different is that each pixel is allowed to have its own vertical scaling with a scalar inverse at each pixel, and also a mean trend, right? So like maybe the mean trend is just a constant, but those constants can be different, like where the Gaussian process wiggles around. But now we want to do the same things, right? But now we'll think about doing this for the whole map at once, for all pixels at once. And this is what I get looking at that Thomas fire from a scaled version of the actual rainfall time series. So this was the peak I-15 for the actual rainfall. Here we have it at half that value, and I think 1.25 times that value. Right, so you can now get just the probability of inundation quite quickly for different rainfall scenarios. And we can also now think about, well, we know this is something my colleague Luke was quite interested in, that that we get some healing to the landscape, that eventually we'll go back to sort of a normal state and the soil won't be so hydrophobic. And he has this Liu et al. Model. It's looking at saturated hydraulic conductivity versus time since the fire. Just a little heuristic model fit to this data. But if we put that into our surrogate framework, now we can see sort of 0 month, 1 month, 2 months, 3 months, et cetera. And we see here that things, and this is quite grainy up here, but that things sort of go back to or hit about a sort of stationary map at about 8 or 9 months. We can also sort of play this game with looking at, so now we have both saturated hydraulic conductivity and the bed friction. And so this is sort of a natural experiment. This is from a different fire, the station fire. And so here's what clear flows look like. The fire occurred here. And for Luke's model, at all of these rainfalls, they looked at parameters that matched the actual observed flow volumes. And so we're again looking at the sort of 2-month and the 14-month, I believe. And now plugging them into our framework, we can get the probability of inundation 2 months post-fire. This is, assuming the same sort of behavior at the Thomas fire as a station fire, but 2 months post-fire and 14 months post-fire. So this isn't a conclusion so much as what can we do with this tool, right? That's the sort of thing that we're looking at. So wrapping up, what's next? So something that the students been working on is thinking about how can we do this ZPPE process everywhere at once, right? For all the pixels at once. So that's something I'm quite interested in. Also thinking about generally for PDCs. Okay, so we have this surrogate tool that we could explore probabilistic models of scenarios, but often, particularly if a volcano doesn't have isn't well cataloged, we don't have data to build an aleatoric model on. But analogs of other volcanoes for what an aleatoric model, say for volume, might look like, I think are going to be quite powerful. A student of mine, Josh Seidman, has been working on this debris flow problem and trying to learn about erosion rates sort of on the fly, right, within the flow, because these are things that really can't be measured in the field. And so he's doing this with a Vecchi approximation for the parallel partial emulator, which is can deal with a really large training data set, which is what we're thinking about here. And he's going to combine that with neural networks. And I should have so I was selling Luke's model, and I believe it's way better than competitors out there. But he was knowing, even if we could get similar volumes, often the erosion pattern doesn't match the erosion pattern that you'd see in reality. So he was seeing things where the sort of edges of the channel would be eroding a whole lot, but the base of the channel wouldn't be eroding enough, right? So we're trying to work on within the simulation, how can we get things sort of through an inversion with this process that better match erosion patterns, but still are getting the debris flow driven by rain. Okay, and then ultimately, of course, what we're interested in is decision support for communities living near hazards, and at least for the debris flow, thinking about the probability of future cascading hazards. Right, so maybe combining sort of aleatory models of burn severity patterns and subsequent flows, or thinking about climate change and future intense rainfalls and burn severities on future potential debris flows. And that is it. Right.
Can use any.
This can.
Okay. I'll assume that people in Zoom can hear us. I don't know if we can check if there are questions from Zoom, but I'll open the floor first to the audience, and then we can check on Zoom. But again, once again, thank you so very much. I think it's been an amazing talk. So many things being done already, and so many things that could be done in the future. Yeah, I think these methods are very powerful, and they have a lot of applications. So I think I'll open up if anyone has questions for Elaine at this point. Okay, no. Otherwise, I can ask a couple of them.
Thank you, Elaine. Thank you very much for your talk. It's, well, more a comment on the last slide that you showed about future ideas, because I missed that point about this Becky approximation. What do you mean that you are intending to replace with neural networks your surrogate models, or?
Yeah, so, and I didn't get into it, but basically what we're thinking about is we still have only a handful of simulations, right? So we're still quite limited on simulations. But then really what we're interested in is flow characteristics driving the entrainment rates. So thinking about the flow velocity or the stream power, maybe the sort of local slope, and also the catchment area above a particular location. As those are, we're thinking about as inputs into our model. And if we sort of collapse the pixels that way, then there's a ton of data, right? Lots and lots of data, way more data than you could deal with. But we also still only have this, in this case, 60, or I think he's working with about 40 simulations, right? So to think about the different simulation parameters, we need a way to sort of fill in what other simulations would look like, which is where this sort of Vecchia PPE comes in. But now we have tons and tons of data that then can be pushed into a neural net. And that's what we're thinking on. It's still a work in progress, but that's what we're looking at.
But you would still rely on your surrogates. I mean, it's just to expand your
The surrogates
data
would be
set
to
and everything.
expand the training data
Okay,
effectively.
fine,
Mhm.
fine. Thank you.
So right, yeah.
Yeah, like having additional data, right, on to which sort of look at outputs, sort of things that can influence outputs that are not in the model parameters, say, right, or maybe they're.
So it's really thinking about, so really what we want to model is what does entrainment look like for a given flow scenario and a given location in the catchment. Because it's something that's not observable in a live flow, of course. But besides perhaps at a few points, but really not effectively not observable. But then if we had models for entrainment based on flow inputs, in addition to the sort of computer model inputs, then we can think about doing an inversion problem where, okay, how well do these match the erosion patterns? How well do they match the volume? And then we can, sort of cull off this giant data set into the data that's really capturing or erosions that are capturing the things that are observable.
Okay, thank you. Sandy?
Thank you very much. So I have a question also related about the analogs for probabilistic scenario models, because you talked about volcanoes that, for example, that we don't have historic catalogs. We don't know what happened. So I was wondering, what are you planning to do in that case? What are your thoughts about that? And as a secondary question to follow up, we're talking, let's say, about volcanoes that are experiencing landslides or caldera collapses. So what happens when we have these kind of scenarios here?
Right. I mean, I think that's so for your second question, then that's where sort of analogs come in, because you'd want to be thinking about, comparing apples to apples. And your first question, we've not done it. We've not done this work for volumes, which I think for distributions of potential volumes, which I think is what would be quite powerful. But we've done this for the mobility metric from for volume versus H over L, right? So there we can think about having, and sort of there it wasn't quite as fancy as of an analog tool, but sort of groupings of similar volcanoes to get that mobility metric, and we could then apply it for a volcano that had maybe 2 or 3 flows at all, right, on the record. And so in that way, we're sort of, and I wish I had a picture of this particular work up, but basically we're saying, okay, so we have these analogs that have a fair bit of data, and then we have the volcano we're interested in with zero or little data. In the case of little data, you can say, well, I'm going to look at these sort of end spectrums where I consider each volcano to be its own unique thing, or I consider them all to come from a common probability distribution. And in the sort of hierarchical approach that we're interested in, you end up sort of splitting the difference, where things are informed somewhat by the larger group, but then also by the particular volcano of interest. So that's the sort of hierarchical approach of sort of sharing the data from the pool, but recognizing that each one is in some way an individual, and balancing between the two to sort of glean the information from the bigger group for the volcano that has little data. If a volcano has no data, right, that's maybe a different question. And there it would probably be thinking just completely relying on analogs, but maybe sort of pooling analogs that are sort of a spectrum of similar to come up with a model.
And in the end, I think that's sort of frontier. I mean, we have just scraped the surface of all of this world, in my opinion, because I mean, there are so many ways in which you could group those volcanoes as analogs in order to do those analyses. I mean, think of a given volcano. Do you group it as, I get all the stratovolcanoes, all the volcanoes that are in that, say, a subduction zone area? Do I group them by geochemistry, combinations of both? So that's really something that, I mean, with the tools that we developed to find those analogs, you could start sort of investigating different hypotheses that would lead you to different statistical models. And then, of course, it would be a matter of also sort of testing against the data that you have. So maybe start with data-rich volcanoes, try these approaches, see if this works or not. And it's not just for PDCs. I mean, one thing that we have been thinking about with Elaine for a while now is sort of using it for the size of eruptions, say VEI. So you try this, and this would be huge, I think, for the volcanological community. Try to play around with these Bayesian hierarchical models and different sets of analogs to get your distributions of VEI given eruption, for instance, or temporal models if the data is there to be used. So yeah, I think analogs are the future. Any other questions from the room? I had one sort of in the frontier thinking. So far, I think we always do our models. So I assume that when you were doing the post-fire debris flows, you were running simulations that affected the topography with erosion and deposition, but then a new round would use the old EM, right? So, right? I mean, you're not using sort of, I mean, a new simulation sort of starts the modeling with the DM that you have for all the simulations, right? So I guess the open question is, how do we deal with changing topography? Is there any hope of trying to deal with that statistically or not?
I'm quite skeptical that you could really deal with change in topography, because you would just sort of have an exponential explosion, of sort of conditioning on different changes for, and even if it was PDCs, like thinking about what could have happened in the interim 5 or 6, say the deposits to change the landscape. Mm-hmm. Right. And so I don't see a way to effectively do that. Mm-hmm. I think maybe an easier but still hard problem would be thinking about PDC or volcanic deposits to lahars, right? That might be something that is a bit more tractable, just thinking about one step, right? So you have, these deposits from the dry season at Fuego, and then the rainy season comes. Can you work with the sort of deposits and landscape you have to inform what lahars would look like? I think that
which-
seems like along those lines, but something that seems plausible to me. I think that really unknown changes in landscape and how that might affect future flows. That seems very, and I don't think we're there.
Yeah, this is a very, very big problem, but especially in sort of very dynamic environments like Fuego or other frequently active volcanoes. But yeah.
I think though, I guess to, sort of devil's advocate, and these aren't hazard maps, but thinking, what our colleague Eliza Calder often says is we're sort of looking for gross features,
Yeah,
and
definitely.
what could happen in, especially if you're thinking about midterm sort of maps in the next 20, 40 years. And so things aren't going to be perfect. Right. You're not going to capture a scenario perfectly, but if you can capture the sort of important gross features, can you provide a useful set of hazard analyses for decision makers? I think that's probably the better goal than trying to get it perfect.
Like major filters, like like overbanking, say, that goes towards A, it's sort of captured by both models, even though they are sort of end members in terms of the rheology, right? But
we've been working on this project for a while, and we knew that the sort of inundation footprints that we're seeing here would look different, but I honestly thought they would be more different, I guess. In the scheme of things, there's certainly more overbaking for Titan and longer runouts for Volk flow, but I suppose I was expecting something a bit more dramatically.
Yeah.
Although, as we're seeing here, there's implication for hazard assessment. They are quite different for that location that's right next to the channel, right? So, and I think that's another interesting thing is not necessarily combining models, but how to think about communicating model-based, so physical model-based hazard analyses that tell you different things to stakeholders. Like how do we explain this to our colleagues at Insimume?
Yeah.
Right. And I think that's another sort of interesting avenue of work in general.
Yeah, definitely. It's so complex. This is just our small bit as volcanologists, and then of course everything sort of explodes when you go into the risk and so many different stakeholders and expertise is involved. And with the PDCs and lahars is something that similar to what we tried to do at Vesuvius, trying to model in PDCs on Tephra, with that sort of estimate volumes in different catchments and how that would affect generating lahars afterwards. And it's interesting as well, this role. For instance, at Fuego, that PDCs are meant to be generated from material that is there. Anything sort of an increase in rainfall for any reason, in principle, should act for erosion in those areas. So it should, in a way, reduce PDC hazard, but of course, it should increase lahar hazard. So these things are, of course, intertwined. And multi-hazard is another super big problem that we need to tackle and address. And we were trying to do it initially, but we found it was too difficult. But how this hazardous phenomena interact between each other is a whole new beast. Okay. Any other questions from the room? Barbara was telling me that people in YouTube may ask questions, but there's no questions there. I don't know in Zoom if there is any. Let's check. So you can see the chat here. Nothing. Okay.
Good.
All right. So we're good with time as well. So thank you very much once again, Elaine, for everything, and